This talk examines the detrimental effects of coupled dissolution precipitation on geochronology. I'm working with Jacqueline Halpin from the University of Tasmania and Tom Raimondo from University of South Australia, along with a range of students and postdocs in a number of tectonic settings and locations. What we're interested in looking at is the effect of melt migration on accessory minerals like monazite and zircon, and to test the reliability of current geochronological interpretations, particularly in the case like shown on this concordia diagram to the right, where individual spot ages spread over tens or hundreds of millions of years. The first part of the talk will focus on the geological process of coupled dissolution precipitation. In the classic experiments by Andrew Putness, they placed potassium bromide crystals in a chlorine-rich fluid. In panel A, a rim develops that's porous. The porosity allows fluid pathways into the core of the crystal. In panel B, the crystal has been completely replaced by a coupled dissolution precipitation. In panel C, with time, the porosity coarsens. And by D, the crystal starts to heal after 12 days. Note that with prolonged exposure to a fluid, that porosity that drives the process can completely heal. They found that the reaction rates are very high with coupled dissolution precipitation. The process is driven by the relative solubility of the minerals in the fluid. And so a mineral will dissolve if the fluid is undersaturated with respect to the mineral. Because we've just dissolved a whole lot of components of the mineral into the fluid, you get local saturation at the interface, and this drives precipitation. And so then the reaction migrates inwards into the crystal, and this happens via porosity in the new minerals. The image to the right shows a tomographic image, a CT scan, of one of these textures. And the yellow areas are the porosity that connects the bulk fluid to the reaction interface. These remind me of anthills. Our research question is whether this process is common in minerals like monazite and zircon that we use for geochronology. We often see these complex textures in cathodoluminescence, like is shown on this zircon on the left. Our new interpretation of these textures is that at the interface of the fluid zircon reaction, the dissolution of those zircon components includes its uranium and lead isotopic character, such that when the new zircon precipitates in coupled dissolution precipitation, it inherits or partly copies that uranium lead isotopic character. And so although the grain has been recrystallized, it's not resetting the age to 0. Depending on the connectivity of the fluid at the interface and the bulk fluid that's driving the process, the cartoons on the right are showing that that communication needs to happen through this recrystallized domain. If the connectivity is high, then there's a good chance the lead can get out, and we might reset the age of our rim domain. If that connectivity is low, then the likelihood of transporting the old uranium lead isotopic character away from the crystallizing parts of the grain is less likely. We think this process creates complex age patterns, like is shown in the upper right. Recall in the colored diagrams at the bottom that with prolonged exposure to the fluid, the new recrystallized grain can homogenize its chemistry and heal the porosity. The process of coupled dissolution precipitation needs to be contrasted with volume diffusion, because many people in geochronology think about closure temperatures in terms of volume diffusion. This happens in the absence of a fluid. It has high activation energies and therefore happens at high temperatures. The components move via the crystal lattice. There's no destruction of the framework, and the rates are quite low for most silicates. With CDP, when we have fluid around, it happens over a broader range of temperatures because of the lower activation energies. It's very fast, and it involves the three steps of dissolving, some transport in the fluid over very tiny scales to quite large scales, and then precipitation. So let's now look at some experiments that we published on in 2020. These experiments were done at Macquarie University with John Adam and a PhD student, Varga. The kind of experiments that have been done with monazite in the past involved a range of fluids. With water and brines, they found that there was little interaction and reaction. With alkali-bearing fluids, they got good core and rim textures to form with this porosity in the outer parts of the grains. And they found changes in textures, chemistry, and geochronology. In the 17 experiments that have been published, 5 of the experiments were able to reset the age of their monazite in experiments with temperatures as low as 450 degrees Celsius. In many of the experiments, an observation of incomplete lead loss, unsupported lead, and in their seminal paper by Grand Home shown in the pictures, they interpreted that they were ablating nanomixtures of the precursor monazite and the zero-aged monazite to produce these smears along concordia. A range of chemical changes are also observed to happen during the process. Our key message looking at these experiments is that the monazite that's precipitated during coupled dissolution precipitation, it can record the age of the recrystallization event, or it can record these inherited ages of the precursor monazite, and it will show these apparent lead loss trends. Our idea was to do experiments involving monazite and melt. We took 2 monazite standards from the University of Adelaide, the AMBAT standard, which is around 520 million years old, and the Mount Garnet standard at 320 million years old. We placed these 2 monazite standards into a natural eutectic granite, and in a couple of the experiments we added some sodium fluoride to speed up the reaction. In the 3-hour experiment with a small amount of sodium fluoride added, we found that the Mount Garnet monazites dissolved and they showed porosity throughout the grain. In the very right is an AMBAT crystal which develops a core rim texture. We interpreted 4 textural types. Textural type 1 in the core of the grain representing the original mineral, through to textural type 4, which are these relatively inclusion poor, clean rims on the grains. In dating these 2 different grains, the 520 AMBAT crystals showed a range of disturbance along the concordia and away from the concordia. These are partly due to mixing with the melt that was frozen in inclusions and potentially ablated in our volume, and so some grains you can see head towards that yellow circle, which is the melt near the grains. For the 320 Mount Garnet age standards, some of these headed towards that melt composition, but also showed lead loss trends heading away from the concordia. A few grains were plotting discordantly down towards the younger end of the diagram. On the very right, you can see that the process in the AMBAT crystal is driving significant chemical changes where the recrystallized or precipitated domains have a very different chemistry to the precursor crystal. Allowing that experiment to continue to 24 hours in this next experiment, we found that the Mount Garnet standard dissolved completely. We couldn't find any evidence of those grains left. The AMBAT standard still had the core rim texture with these domains T1 to T4, but the rim domains were getting larger, possibly by the dissolution of the Mount Garnet standard and migration of that material to form rims and euhedral crystals within the experiment. We found no relics of the 320 age Mount Garnet standard. After 24 hours, we saw a significant proportion of those T4 rim domains as showing us relatively reset ages. Not perfectly reset to 0, but quite close to 0, and certainly on a trend that's heading towards 0, 2 million years old. The problem with those grains is that they didn't reset neatly to 0. they still had some history of that precursor lead and uranium isotopic story in them. The other grains, the other analysis of the domains T2 and T3, they spread out along concordia over 200 or 300 million years. In a natural sample here from Central Australia that one of our students have been working on, this is a sample from a shear zone. The precursor rock looks like it's something in the range of 1660 million years old. Some of those precursor grains or domains of the grains have experienced lead loss on a discord, the light blue symbols heading away from that 1660 position. The grains that are young and potentially interpreted as new don't form a tight cluster at the young end of the spectrum. Instead, they spread over a couple of 100 million years. The diagram at the top is showing the complexity in the monazite internal structure. So what have people interpreted in natural rocks, and what have they published? We can find lots of examples of complex textures that are indicative of coupled dissolution precipitation, and people report this as their interpretation. Their uranium-lead data is also complex, and so how we treat that data and how we interpret that data is quite fundamental to understanding the process and what it's telling us about geological processes. Everyone, including me until now, assumed that the ages we were getting were always geologically meaningful. In an example here from Western Australia, monazite that formed in low-grade metamorphic rocks less than 400 degrees Celsius showed quite convincing overgrowth or rim textures, and the age patterns were quite distinct between the cores and the rims. And so here we seem to have either formed an overgrowth proper or properly reset the core age to a new rim age. In this interesting paper from 2012, they looked at pegmatitic monazite in 3 different locations. They dated the samples with electron microprobe chemical dating, and they found that the secondary monazite was generally younger than the primary monazite, but not with a very tidy age range. In one of the samples, in the middle, they found that the age of the secondary monazite was actually older than the precursor monazite, which was a problem. In the same samples, they dated the same grains with laser ablation methods, where they could start to look at the different isotopic ratios. In the various diagrams here, we can see some of the same patterns that we saw in our experiments. Incorporation of common lead, some evidence of lead loss, but also some evidence of lead gain in the middle sample. Another example here from Antarctica, where the ages ranged from 1030 to 880 within a sample and also between samples. And the interpretation was that the geochronology was consistent with the evolution proposed elsewhere in the Rayner complex, but texturally, if we look at some of the pictures that were presented in this work, there is evidence of coupled dissolution precipitation. Things like the porosity in the cores of some of the grains, and things like the inward penetrating lobate rims as shown in the chemical diagram at the bottom. In Australia, the Musgrave inlier, the monazites are quite complicated and look like they've experienced some dissolution. The interpretation here was that the age spread was geologically meaningful, and the team interpreted high temperature supersolidus conditions were maintained for more than 70 million years. In an example from Madagascar by an American team, they looked at both monazite and zircon. So firstly, the monazite, they saw these spreads in ages as being geologically meaningful. They interpreted that these spread of ages recorded an 80 million year time period of metamorphism. The zircon data, you can see, are quite complicated. Individual grains show a range of ages for similar textures, and yet still the common interpretation with these datasets is that they're telling us something about the timescales, the long timescales of metamorphism. In Sri Lanka, this team compiled more than 1,000 zircon ages from this area. Again, they interpreted the age spread over 100 million years to be geologically meaningful, indicating that there was possibly a long-lived high-temperature metamorphic event. Our point is that these complex patterns can form in hours in the experiments. And so is it true that these age patterns in natural rocks really require tens or hundreds of millions of years to develop? Stepping to zircon and the work we've done in the past on zircon, this is an example of the Mawson charnocote, and I showed the complex textures on the left early in the talk. The age spread that we get over a couple of 100 million years, between 690 and 1048, our interpretation back in 2012 was that around 1050 was probably the emplacement age, or at least a minimum emplacement age, and everything else in the age pattern was some sort of mysterious lead loss event. In 2012, we wrote that we argued against complete recrystallization, as this, in brackets coupled dissolution precipitation, it should expel lead and completely reset the uranium lead age and remove all trace of primary zoning. I think back then we got it wrong. I think this process of coupled dissolution precipitation can form such an ultra-local chemical environment at the dissolution precipitation front that the uranium lead character of the precursor grain can get copied, or at least partly copied, to form these complex spreads in ages. So now what we would interpret is that those 1050 aged grains are just xenochrys. And texturally, in some samples, like in the BSE image here we went and collected last year, we can find evidence for porosity in the cores of some of the grains and in trails running through some of the grains. We now think that this porosity is telling us that there's been almost complete coupled dissolution precipitation replacement of these precursor grains. They're xenochrys. And so the ages are imperfectly inherited from the xenochrys. The key message here is that zircon that's been affected by this process, it doesn't necessarily faithfully record an accurate age of the recrystallization event. Here, it's probably around a 530 Pan-African age is the true age of the Mawson charnocote. This made me go back and look at some other work that I had done previously. So in 2016, with Luke Milan from the University of New England, we published some work from Fiordland, New Zealand. After discovering these issues with geochronology, we went back and looked at some of his backscatter images of his grains. And you can see here that there is abundant evidence of this porosity, which I think is a hallmark of coupled dissolution precipitation. So the age spread over 10 or 15 million years that we saw in nearly all of his samples possibly represents the process rather than anything significant about the geological timescales. In a paper here published by Saman et al., they looked at zircon in some pegmatitic rocks, and again this inclusion-rich and porosity-rich zircon 2 is interpreted to form through coupled dissolution precipitation. Here, the ages of zircon 1 and zircon 2 were roughly the same. Nonetheless, in some of their geochemical data, they see some evidence for common lead being incorporated, and they need to reject some outliers in order to make their age interpretation. In an example here from some oceanic gabbros drilled at a core complex, there are two types of zircons found in 20 different samples of oceanic gabbro. 19 of the samples showed the relatively clean zircons shown in the lower left. They give an age of 12.76. One sample showed evidence of coupled dissolution precipitation shown here on the right, and the age was slightly younger. The 12 million year age matched the age of the magnetic anomalies, and so the CDP event is what was dating the age of the seafloor in this area. In very old things, here's some Hadean zircons, where very detailed chemical mapping of lead-207 shows that it forms clusters and variation at the grain scale. Depending on which part of the grain they integrate the data over, they can get any of those ellipses on the concordia that spread over a few 100 million years. These complexities in detailed chemistry of the grain, we believe, are formed through coupled dissolution precipitation and migration of these components into different domains of the grain. So now we're starting to step away from convention. In a paper that we published this year, we're putting out a new interpretation where magmas that are undersaturated in zirconium are going to be dominated by xenocrystic zircon cargo. They're not going to have enough zirconium to be growing their own new zircon. The modification of these zircon xenocrysts by coupled dissolution precipitation will modify the ages towards the magmatic age. So in both of these granitic samples, we interpreted a 1150 magmatic age based on the regional picture. But you can see that there's not a lot of evidence in the actual zircon data itself because we interpret most of it is xenocrystic. In the cartoon on the right, we've tried to show the process of progressive replacement that ends up producing quite a complex zircon internal texture that's inclusion rich in BSE and CL images. So our final message is, when should we worry about this process being a problem for our geochronology? It's when we see microstructures that are indicative of former coupled dissolution precipitation. We might see core rim textures with or without the inclusions that are inferred to have pseudomorphed a former fluid-filled porosity. When we see inward penetrating curved boundaries between core and rim domains, and we need to be particularly wary that it's possible in cryptic cases that the whole grain can get replaced by coupled dissolution precipitation, and this can leave a relatively homogeneous texture with a complex age pattern. Thank you. I'll open it to questions.